All right, so today and tomorrow we're going to take a look at 11.2, which is on what's called a series. So a series is when you add up all the numbers in a sequence. So finite. Can somebody remind me again what finite means? Whether it's a finite sequence or a finite series, which is same meaning.
It stops.
Yeah, it stops. There's a certain amount of terms, and then you're done. So do you think you could add up all the numbers in a finite series? Yeah, even if there's a billion of them, you can add them, or a computer can add them. It doesn't matter. It stops somewhere. A little bit more interesting idea is an infinite series. So we're not going to talk too much about that today, but tomorrow we're going to look at the idea, can you add up infinitely many numbers and actually get an answer? And it depends sometimes. It depends on the numbers you're adding up, right? But obviously you can't add up infinitely many numbers the standard way you would think about it, because you can't add an infinite amount of things. So we've got to figure out a way, if we're going to deal with an infinite series, how do we add up infinitely many things without actually doing it? What's kind of like a shortcut or something to figure that out? And we'll talk more about that tomorrow. All right, so yesterday we used this notation, a lowercase letter and then a subscript to represent a sequence or a specific term in a sequence. Okay, so what I'm going to do is let's write out the first few terms in this sequence. Okay, so sequence A. And I'm just going to write out the first few terms. The way you do it is you just start with the number 1, you plug it in for n, and then do the calculation out. So if we plug in 1, what's 2 times 1? 2 minus 1? 1, and then squared? 1. So the first term in sequence A is 1. The second term would be what? 9. Okay, the third term would be 25. And let's do one more. The fourth term would be 8 minus 1 is 7. Squared is 49. Okay. When I look at it like that, you might start to see a pattern, but if you write it like this, 1 squared, 3 squared, 5 squared, 7 squared, then I think you can see the pattern a little easier. It's odd numbers squared. So what I want to do now is look at what we call sums. And we're going to use the notation S sub n, okay, capital S subscript n. And what that notation is going to mean is the sum of the first n terms. So S sub 1 would be the sum of the first term. There's not really much to add there. So if I wanted to find the sum of the first term in sequence A, what would the sum be? It would just be 1. It's the only term. Or you could write 1 squared. It's the same thing. Okay. Now if I want to look at S sub 2, okay, I go back to my sequence, and I would find the sum of the first 2 terms, okay, which would be how much? 10. Right, so we could kind of simplify this. We get 1, 10. S sub 3 would be the sum of the first 3 terms. 1 squared plus 3 squared plus 5 squared, which would be how much? 35. And then if you wanted to write down the sum of the first n terms, well, it would be the first term plus the second term plus the third term plus the fourth term, all the way up to the nth term. And that's the formula for the nth term. Now, if you look at this list of numbers here, let's even do one more. The fourth term. So we already know the first 3 add up to 35. What's 35 plus 49? 84. Okay, so now if you look at all the numbers I circled, okay, I'm going to make a list of them. Okay, I'm going to make a new sequence, 1, 10, 35, 84. Each number in that sequence is a partial sum. That's S1, S2, S3, S4. Now, if we can find a pattern in these numbers, okay, that I just circled, then you can add up any amount of numbers you want without doing it by hand. Like if I said to find S sub 105, that means to add up the first 105 terms in sequence A. You definitely don't want to do out 105 terms and then add them up. There's got to be a way to figure out a pattern of the kind of answers we're getting right here. Okay? And there is. Okay? And we'll talk a little bit about that today. Okay? So any question on the idea of what we call a partial sum? Okay? We call it partial because, and I think I'm going to write that down in a little bit, but because we're not adding up maybe all the terms in the sequence, maybe you're just adding up the first couple, or the first 3, or the first 4. Okay. So each individual term, okay, that I had on this page, S sub 1, S sub 2, S sub 3, and S sub 4, those are finite sums. Okay, we added 4 things to get that number. 4 is a finite number. It has an end. It's just 4 things. To get this one, we added 3 things. We didn't add infinitely many things to get 35. We only added 3. So each sum there is finite. Even if you add up the first billion terms, that's still finite. Okay, there's a certain amount of terms that you added together to get that partial sum. So the next thing I'm talking about is writing down a sequence of partial sums. That's exactly what I had right here. 1, 10, 35, 84. That's a sequence. And each term in the sequence is a sum. And that's what I'm explaining right there. And really, the goal is to figure out a pattern in that sequence. Because we don't want to try adding up a bunch of things by hand. We got to figure out formulas to do it quicker. Right? And here I'm just explaining in general. If you had any sequence, the first partial sum is basically just the first term. The second partial sum is the sum of the first 2 terms. The third partial sum is the sum of the first 3 terms. The 50th partial sum would be the sum of the first 50 terms. And then the nth partial sum would be the sum of the first n terms. So, any questions on the idea of a sequence where each term in the sequence is a sum? Now, sometimes it's easy to figure out a formula for a sequence S sub n. Sometimes it's not. It can be extremely hard. In general, we're going to look at patterns that are pretty well-known patterns, and there's formulas for doing it. Okay, you're not going to have to try to invent or figure out something new on the test that we don't talk about in class. Everybody have that? Okay. So what I want to show you next is a kind of a short way. What if I wanted to write down the sum of the first 50 terms using notation like this? I don't want to write A1 plus A2 all the way to A50. It's going to take a long time. So I'm going to show you a compact way to write stuff like that down. Now, the notation I'm about to show you, it's called sigma notation. And the notation itself, it's a short way to write things down, but it doesn't actually speed up any kind of calculations. All that it is it's a short way to write stuff down. If you actually want to do out the calculation, you still have to do the whole thing until I show you a shortcut in a little bit. Okay, so let's say you wanted to add up the first n terms in a sequence. And you wanted to represent that with some kind of notation without writing out A1 plus A2 plus A3 plus A4. Okay. What you could write is that. So S sub n stands for the nth partial sum. Okay. Over here on the right, this is the formula for the sequence. So if I go back, I'm going to go back for a second just to the first page. But that A sub k that I just circled would be that right there. It's the formula that's generating the numbers you're going to add up. Okay, so they got to give you that. And then they have to tell you where you're going to start. What term do you want to start at? In this case, we're saying, I want you to add up numbers, and I want you to start with the first term. Okay, so this bottom one kind of tells you where to start. And the top says, well, where do you want to end? Do you want to add up the first 7 terms? Then put a 7 at the top. Do you want to add up the first 50? Put a 50. And what you do to figure out the numbers you're going to add up is you start with the number 1, plug it into your sequence, do the arithmetic, write it down. Then go to the next number. Change k to 2. Plug in a 2 into your formula. Do the arithmetic. Write that answer down. And then you keep doing that all the way up to the last number they want you to plug in. And then you add everything up. That's what this symbol means. That's a capital Greek letter, sigma. Okay, so the way you pronounce that is it's the sum from k equals 1 to n, from the first term to the nth term, of my sequence, A sub k. Again, they have to give you an actual sequence to work with. And k is what we call the index of the summation. Basically, it's the variable. Okay. You don't have to use the exact letters that I've used up here, but what you do have to do is make sure the letter that you use at the bottom is the same letter you use in your sequence. Those letters have to be the same. Okay, so here's an example. This one is having you add up the first 5 terms in the sequence 2k plus 3. Okay, so let's just do this out. We'll expand it. Start with k equals 1, plug it in, and write the answer down. If you plug in 1 for k,
That's it, S5.
S sub 5, yep. What do you get if you plug in 1 for k in the formula 2k plus 3? 5. And I'm going to put a plus sign. Why do I put a plus sign? Because of that capital Greek letter. Sometimes as I start writing them, they start to look a little sloppy, but just to kind of show you exactly how it should look. That's what it should look like. All right. Now if you plug in a 2, what would be your next term? 7. Plug in a 3, a 4. And now we stop at 5 because of that number right there. What would be my last term? 13. And now you add those all up if you want to know the answer. So again, it's a short way to represent all of this information, but it doesn't actually speed up the calculation. You still have to do the whole thing out until I show you some kind of shortcut. Okay. Any questions on that idea? That's called expanding a summation, expanding it out. And that's basically what I just explained to you. So when you use what we have up above, that's sigma notation. When you do it the way I wrote it below, that's expanded notation. So sigma notation, expanded notation. And the index doesn't always have to start at 1. You can start the index wherever you want. So I'm going to go back to the formula we just had, and I want to see if you can come up with a different way to write the same thing, something that's equivalent. Okay, so let's take this one. And let me start it at 0. So if you change the bottom number, it's going to change everything else. If I start at 0, where do you think I'm going to end? I'm going to end at 4. But now I have to adjust this formula a little bit. Specifically, I have to adjust that. So what did I do to my k value in the sigma part? I lowered it by 1. So we have to balance that out on this side of it. So if I made k 1 smaller, what do you think I'm going to do to k here? Well, that wouldn't balance it.
You want to make it 1 bigger.
We have to make it 1 bigger, like this. And if I distribute that out, I get 2k plus 5. Now watch what happens if you plug in 0. And let's write down what we get. What's 2 times 0?
0.
Plus 5? There's the 5. It's the same term we started with before. If you let k equal 1, 2 times 1 is 2. 2 plus 5, 7. There's your second term. So we just created a new formula that starts at 0 and goes to 4, but it's exactly the same thing. So what this is called is re-indexing a summation. And the idea is, in this part, you have to balance it with that part. So if you make a number smaller in this part, you have to make it bigger in the part on the right by exactly the same amount. Right? That's why I put the k plus 1 in parentheses when we made k 1 bigger, because it's a distributive. You just have to remember that. Right? And the reason I show you that is because on a test, I might give you a pattern, and you might come up with a formula for it. But maybe the formula you come up with, you decided to start at 1. But if it's a multiple choice question, maybe I decided to start at 0. You just have to be able to figure out that your answer and my answer, if you re-index, are the same thing. Okay. Any questions on that? 1 is the most common place to start. 0, you do see that a little bit too. But generally, 1 and 0 are the most common. Okay, this one, it's asking us to expand the sum, but it's asking us to go to n. So what we do for that is usually write out the first 3 or 4 terms, put a dot, 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 and then put the nth term. Okay, first thing I want to ask, is this a finite sum or infinite?
Infinite.
Why do you say infinite?
Because it goes to the end term, which is,
Is the nth term infinite, or is it an actual term somewhere?
actual term.
It's an actual term somewhere. We don't know if it's the millionth term or the trillionth term, but it is an actual term. If this was infinite, you would see that on top. Okay? And we're not going to look at infinite till tomorrow. All right, so let's expand this out. Okay? What's going to be my first term here? And let's just leave it as something squared. The first term would be 5 squared. If you leave it squared, you'll see the pattern a little easier and just a little quicker. How about the second term? Yep, 7 squared. Third term? 9 squared. And now, at this point, you've kind of established what's happening. 5, 7, 9, 11, all squared. We can put a dot, dot, dot. And now we're going to end at the nth term. So what would you plug in for k? You'd plug in n. 2n plus 3 squared. So that is a finite sum. It ends right at the last term with n. Okay. Any questions on expanding that sum? If you want to just do more than 2. Do at least 3. If you want to do a fourth one, that's fine. But 3 is good to at least show the pattern. All right, so we're going to look at some properties with summations. Okay, basically, these properties are going to be used to either take summations that are separate and combine them. So if you had like 2 summations, how can we combine them? Or we can take one that's combined and we can separate it out, like that. That's a summation that's been separated. It could actually be separated a little bit more into 2 parts at the first one and into 3 parts with the second one. All right, so the first rule says that if you have 2 sequences, okay, sequence A and sequence B, and you want to add them up, okay, and I'm going to show you this with some actual numbers so you can see it. If you want to add up all the numbers in sequence A plus all the numbers in sequence B, there's 2 ways to do it. First, you can add the numbers in each sequences. The first term in sequence A plus the first term in sequence B. Write that down. The second term in A, second term in B. Write that down. Third term in A, third term in B. Then write that down. And then take everything I just said to write down and add them up. Or, if you want to add up all the numbers in sequence A and B, the second way to do it is to first add up every number in the first sequence. Write that down. Add up every number in the second sequence. Write that down. And then add those 2 together. Okay, so I'm going to show you with actual numbers. And I'm going to do very short. I'm just going to do like three terms. Let sequence A be 1, 3, 5. Sequence B, 2, 4, 6. Okay, let's start by doing A sub k plus B sub k. Okay, so to do that, we're going to create a new sequence, and we're just going to add term by term. Okay, what's 1 plus 2? 3. 3 plus 4? 7. 5 plus 6? 11. That's the sequence A sub k plus B sub k. Now, we just figured this out. Now I'm going to add up everything from 1 to 3, because I only have 3 terms. Okay, so let's add them up. Let's see, I'll put it over here. The sum, A sub k plus B sub k. What's 3 plus 7? Plus 11. 21. Okay, so doing it the way on the left, we get 21. Okay, let's do it the way on the right. This way says take sequence A and add everything up in sequence A first. What's 1 plus 3 plus 5? 9. Plus, now add up everything in sequence B. What's 2 plus 4 plus 6? 12. And what's 9 plus 12? So no matter which way you do it, you get the same answer. Okay. Any questions on that? And rule 2, you basically could just take rule 1 and put plus or minus if you don't want to rewrite the whole thing. It works for addition, it works for subtraction. Okay, so I'm not going to go through it with rule 2 because it's the same thing. Notice when you take and rewrite it, your index has to stay the same on everything. It starts at 1, Still starts at 1, still starts at 1. Ends at n, it ends at n, they end at n. Okay? Indexes have to stay the same. If you want to combine two sums and they have different indexes, the first thing you have to do is make the indices the same. Okay? I don't think I'm going to give you any like that. If I want you to combine these, I'm usually going to start them at the same index. Okay, and the third rule says if you want to multiply a sequence by a constant, you can either multiply each term in the sequence by a constant and then add them up, or do it the other way around. Add them up first and then multiply after. So let's take the sequence 1, 3, 5 and try that. Let's do it with, I don't know, let's just pick a number for C. Let's let C equal 4. Okay, sequence A sub k was 1, 3, 5. So think of it, it's like distributive property. You're multiplying every number in the sequence by 4. Okay, so what would that make my sequence if I do that? 4, 12, 20. That's this. Now the next part, add them all up. 4 and 12 gives me how much? And 16 and 20? 36. That's one way to multiply a sequence by a constant. Now let's try it this way. This way, the first thing I'm going to do is I'm going to add up everything in A sub k first. So my constant is 4. And what do you get if you add up everything in A sub k? 1 plus 3 plus 5. 9. And then if you do 4 times 9, you get 36. I like it the second way. I think that's quicker because doing it the first way, you have to multiply every number. Doing it the second way, you add them up and then you just multiply one time. And I think adding is quicker than multiplying, but it turns out the same. Okay, any questions on that? Okay, so we can use that idea to combine these two sums into a single sum. Okay, this is going to be rule number 1. You're basically going to take A sub k plus B sub k and just write a single summation sign. So you're going to take this, you're going to add to that, and you're just going to write a single summation. So if I combine the two things that I just circled, the two sequences, okay, pretend that's AK, P sub k. Okay. What do you get when you combine those two together? Yeah, you get 6k squared. Yep, minus 2k. Plus 3. Perfect. That's it. Any questions on how we combine those two summations into one? Just like combining like terms. Now, if you wanted to actually do this out, it still doesn't speed anything up. We still don't know a fast way to do this out. There is. That's what I'll show you next. It's not bad if you only had to do it from, say, 1 to 10. You could figure out 10 terms and add them up. That's not going to take too long. But if you want to go, say, 1 to 1,000, we got to get a better way than doing it by hand. Okay. So this is what I've been saying all class. Summation, sigma notation is a compact way of writing things. But if you actually want the result, you still got to do the whole thing out by hand. Okay. And we're going to look at this one. This is a good one to start with because it's not the simplest case, but it also doesn't involve any squaring or cubing or anything too complicated. So what this formula is, this is the formula for adding up the first 10 integers. When you plug in your number, into your formula, there really isn't a lot of arithmetic to do out. When you plug the number in, that's the answer. Okay, so let's write out the first few sums and see if we can come up with a pattern for the sequence of partial sums. Okay, so using this formula, we're adding up the first n integers. So the sequence would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You're as high as you want to go. Okay, what would be the sum of the first number in that sequence? 1. What would be the sum of the first two numbers? 3. How about the sum of the first three numbers? 6. The sum of the first four numbers? 10. First five numbers? First six numbers? 21. And let's do one more. 28. That list of numbers I just created, those are special numbers. Does anybody know what kind of numbers those are? If you think about representing them as dots, think about like the number 3 as 3 dots or the number 6 as 6 dots. You can arrange the dots in a certain pattern. Kind of like a pyramid. Yeah, these are called triangular numbers. 1 is kind of an exception, but if you look at 3, I should put it right next to it. There's 3. There's 6. There's 10. So because you can arrange that many dots in a triangular pattern, they're called triangular numbers. Okay? Nice fact, but it doesn't really help us to do what we want to do. So we want to figure out a pattern in that list of numbers. Did anybody see a pattern? 1, 3, 6, 10, 15, 21. Yeah?
You add the number of the term that you have to the previous term. So like for term 2, you add 2 to 1. And for term 3, you would add 3 to 3. And for term 4, you add 4 to 6.
So yeah, you keep adding one more each time. So to get from here to here, that's a plus 2. That's a plus 3. That's a plus 4. Then a plus 5, plus 6. So there's a pattern, but it's not the same number you're adding over and over. If it was the same number over and over, what kind of sequence would that be? Arithmetic. Yep. But it's not. It's not the same number. So, but if you can find a pattern where you're adding, and what you're adding by is consistently changing, it doesn't make sense. It's changing the same amount, changing by 1 each time. Let me show you something you can do. Let's make a row of these numbers. 1, 3, 6, 10, 15, 21, 28. And I want to find the differences between them. And I want to go start with the right number and subtract the left number. What's 3 minus 1? 2. 6 minus 3? 3. And then that's 4, 5, 6, 7. Do it again. What's 3 minus 2? 1. 4 minus 3? 1. They're all 1s. When you get to a row of constants like that, what that tells you is you have a polynomial pattern. Polynomial means it's something like, could be 2n squared plus 3, or 5n cubed plus 7. Okay? It's something to a power, and it could be plus or minus something in there as well. And how many times did we have to do this process to get to a row that was all the same? Twice. We had to do it 2 times. So what that tells me is the formula is going to involve something squared. If I had to do it 3 times to get to a constant, it would involve something cubed. Now, I know it involves something squared, but I still don't know, is it like something squared plus 6? You know, I still don't know that part. So what I can do, now that I know it's something squared, is go back to these numbers. Think of them as coordinates. Okay? 1, 1, 2, 3, 3, 6, 4, 10, 5, 15. So somehow you take the number 5 and it turns into 15. You take the number 6, it turns into 21. There's something you can do with the number 6 to turn it into 21. Okay? And you might say, well, don't you just triple it? 5 times 3 is 15, but then 6 times 3 is not 21. So it's not just tripling it. Okay. And I'm going to show you something you can do. So if you go to Stat, go to Edit, and type in all those coordinates. You don't even need all of them. If you just type in a few, that's enough. Okay, and 1, 1, 2, 3, 3, 6, 4, 10, 5, 15. I think we've done typing points in like this before. I think we did maybe way back. And now I'm going to press the Stat button. And I'm going to calculate what's called a regression line. It's going to find a line or a curve, whatever it happens to be, that goes exactly through those points. And I already know something about my line, or curve in this case. I know that it has to be quadratic. Okay? It has to be something to the second power. So any question on how I know that it's quadratic? That's from this, we call this like difference tree right here. So I'm going to tell the calculator to take the numbers that I just put in and look for a quadratic pattern. Okay? And the calculator is going to find a quadratic pattern. Okay? I got to tell it what type to look for, so I have to know that first. Okay? It's going to use that first list for my x's, the second list for my y's. That's exactly how I typed it in. So I just go to calculate. And it says the formula is 1/2, and I use the letter n. 1/2 n squared plus 1/2 n, and there's no constant. Let's try it. Let's plug in 4. What's 4 squared? 16, half of 16, plus half of 4. 2, and 8 plus 2, there's your 10. Okay. Try one more. Let's try 5. 5 squared is 25, and then half of 25, 12.5, plus half of 5 again, 2.5, 12.5 plus 2.5, there's your 15. All right, so the calculator was able to help us figure out a pattern. And the calculator can figure out any polynomial pattern for you up to, this calculator can go up to a 4th degree polynomial. Right? So if you had a list of numbers and you had to subtract 4 times to get a row of constants, the calculator could still figure out the pattern. But beyond 4th, it can't, this calculator can't do it. Okay? But that's our formula. What do both of these terms have in common for constants? They both have a half. So one thing you can do is factor it out. It's n squared plus n, and then take half of it. Now, if you multiply something by a half, what's the same as that dividing by? 2. So usually we see the formula written this way. N squared plus n over 2. So what we just figured out is a formula to add up the first n integers. We didn't prove that it works, but it worked for the first 7. Right? You know that. So like let's say you wanted me to add up the first 1,000 integers. I would just do 1,000 squared plus 1,000 and divide it by 2. And I wouldn't have to do it out. So that's a shortcut. And there's several shortcuts. Okay, I'm only going to show you like 3, maybe 4. Okay, and these are all formulas that will convert something that's in sigma notation, like that, to a formula that you can work with a lot easier. So what I circled at the bottom and what I circled at the very top, they're the same thing. The top one is a nice way to write things, but it doesn't speed up any work. The bottom one speeds up the work. Okay, but this is very tricky to figure out. If you don't have a graphing calculator, it's kind of hard to figure out. Okay, so the one we just did, we're actually going to look at that as the second one. That's the second easiest one. There is one that's a little easier than the one we just did. And this says you're adding up from 1 to n a constant. Okay. So where's the k on this right-hand side? Every other one we do is going to have k's on the right-hand side. But where's the k on that one? It's what? It's not there. Okay, you're adding up a constant. So that would look something like that. So if you wanted to do this out, what do you get if you plug in 1 for k right there? Three. Plus. What do you get if you plug in 2 for k? 3. There's nowhere to plug in k. And if you want to plug in 3 for k, 4 for k, and 5 for k. You're just adding up the same number over and over. What does that come out to? 3 what? Not 3 to a power, but we're on the right track. I want you to think of it that way. Don't think of it as 15. 3, exactly. In this case, it's 3 times 5. You're adding up the number 3 5 times. You're adding up the number c n times. C times n. Okay, so that's one step easier than the one we just did. Just adding up a constant over and over. Okay, the next formula, I think that's the one I just showed you. And I think you could rewrite it. Yeah, it's the same thing. If you just distribute that out, it's n squared plus n. That's what we just did. Okay, but that's the formula for adding up the first n integers. 1 plus 2 plus 3 plus 4 plus 5, as high as you want to go. Okay. Now the other formula I'm going to show you, I'm not going to go through the whole process and how you figure it out. But this is the formula for the sum of adding up the first n perfect squares. 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, as high as you want to go. It's n times n plus 1 times 2n plus 1 over 6. Now, if you FOILed everything out that's in the top, what would be the degree of that polynomial? What would be the degree? No, it would be squared. Number 3. Josh? Cubed. Yeah. If you just FOILed it out, you have n 3 times, so eventually they're all going to multiply together at some point. It would be n cubed. So this is a cubic pattern. If you wanted to add up the first n perfect cubes, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed, all the way up as high as you want to go. I'm going to show you the pattern. But what degree do you think it's going to be? It's going to be a 4th degree. And actually, I think it looks a little simpler than the one above it. There's not as many factors in the numerator. It's n squared times n plus 1 squared over 4. And you could come up with formulas all day. I mean, you could come up with formulas. What if you want to add up the first n numbers to the fourth power? 1 to the fourth plus 2 to the fourth plus 3 to the fourth plus 4 to the fourth. There's a formula for that too. But we're not going to go through that. So all of these formulas you could figure out on the graphing calculator. Maybe it wouldn't give it to you nice and factored like this, but it would give you the formula. Anything beyond this, and the calculator can't give you. Okay. All right, so let's look at this one. And I want to simplify this sigma notation. So when I'm done, I don't want to have sigma anymore. I just want to have a polynomial, like 3n cubed plus 4n minus 7. I want a formula. So, first thing I want to do is split this up. How many sigmas would this split up into? 2. It's going to split up into k equals 1 to n plus another k equals 1 to n. And let's do the last one. That one's a little quicker. That's just going to be a 3. Now, this, it's a negative 2k. You're multiplying by a constant. When we have that, remember the third rule. Where was it? You can take that constant and put it in front. So how would the first sigma look? Okay, right there. So now from here, it's just substitution. Okay. This, the sum from k equals 1 to n of k, we just had on the other page. Right here. The sum from k equals 1 to n of k. So we can substitute in what I just circled in red for what I circled in red there. So it's negative 2 times, and if you know, maybe we can put them both on the screen at the same time. n plus 1 over 2. n plus 1 over 2. Okay, that's the first one. Plus, what's the sum of k equals 1 to n of 3? n. You're adding up the number 3 n times. That's that rule right there. Just replace c with 3. So 3n. So this part's done. Okay. The first part, we got to combine like terms and distribute. But basically, as far as substituting in for sigma, we're done. Now just simplify it. So when I multiply here, what would cancel out? The 2's. Not the negative, but the 2's cancel out. And now I can distribute the negative along with the n. Those two things are together. To that and to that. So what's negative n times n? Negative n squared. And what's negative n times positive 1? Negative n plus 3n.
Oh, less. So loud.
Yeah. So now the last step, we cancel, just combine your like terms. Negative n squared. Oops. And what's negative n plus 3n? 2n. And that's your answer. So now if you wanted to add up, say the first 100 terms in this sequence, you don't have to do any of them out. All you have to do is plug the number 100 in here, and that's it. So it's a fast way to add up a lot of terms. Any questions on that? All right, let's just, I don't want to go through the whole thing on this one because some of the distributive and multiplying takes a while. Let's just split it up and get to the point where you substitute in the right formula. How many sigmas is that going to break up into? 3. It's going to be k equals 1 to n plus another one. And then the last one is going to be minus. Hey, what's the first one going to be?
2 on the outside.
Yep.
And then k squared.
Okay, so you're going to have to look up the formula for adding up the perfect squares. Okay, and we have that right there. Okay, so that's the first formula you would substitute in. What's the second sigma going to look like?
And then 5 on the outside. And then k.
Okay, there. So then you're going to have to look up the formula for adding up from 1 to n of the first n integers. We've got that right there. So what I just circled, that's the second thing you're going to plug in. And then the third thing, it's just a minus 2, so I could do the last term very quickly. It's minus 2n. Okay. The other two, especially the squared one, you're going to have a little bit of distributive property in combining like terms, so it's going to take a little bit. But any question on what you would substitute for that and for that? Okay, I wouldn't give you cubed on a test. Cubed just takes really, really long. Just a lot of algebra. Okay, so you don't have to worry about anything higher than squared. And even squared takes a little while. All right, so the last thing we're going to look at is how can we quickly add up all the terms in a geometric sequence. Okay, the sequences that we were just looking at are not geometric. But there is a quick way to add up all the terms in a geometric sequence. And once I show you that formula, we don't have to go through how to find it ever again. So the first thing I'm going to write down, and I kind of have to give you a hint on how to do this, because it's a little tricky to come up with this on your own. But I'm going to write down the nth partial sum, which means I have the first term plus the second term plus the third term. Okay, that's a geometric sequence. Why is it geometric? Because look at what I'm doing. How did I get from A1 to A1R? What did I do? I multiplied by r. So I did times r. And then what did I do to get to the next one? I multiplied by r again. So if you keep multiplying by the same number, that's geometric. And I can even write out a couple other terms if you want to see them. Cubed. All the way up to the last term. And we talked about yesterday why it's an n minus 1 and not an n. So if you watch the video, you can see that. Now, I'm going to take every term in sequence S sub n, and I'm going to multiply it by r. And I'm going to write the same thing down again. So what is the first term going to become? A1, A sub 1, r. How about the second term? A sub 1, r squared. Plus a sub 1, r cubed, plus a sub 1, r to the fourth, and a bunch of other ones, all the way up until the last one. What's the last one going to become? R to the n. Yep. Okay. Now, something kind of interesting happens if I subtract those two things. If you notice, they have a lot of terms in common. They're kind of at a different spot. But there's a lot of terms that are going to be in common here. So if we subtract them, let's look at this term. Does this term appear in both sequences? Yes. So if you subtract them, that term would cancel out. How about a sub 1r squared? Does that appear in both? Yes. So if you subtract them, that would cancel out. That would cancel out. In fact, everything would cancel out except the first term from the first sequence, because there's no a sub 1 in the bottom, and the last term in that sequence, because there's no, this is the last term here. There's nothing after it to cancel out with. So what you'd be left with is this. If you subtract those two sequences, you'd be left with the first term in the top minus the second term, or the last term in the bottom. And my goal when I'm done is to have something like this. I want a formula for the nth partial sum. So I want to get S sub n by itself. Since S sub n appears in both spots on the left, what could I do with it? Oh, wait a minute, did I cancel out? I think we're okay. So what could I do with that S sub n? Since it appears in both spots. We can't cancel it out, but we can something it out, factor it out. So we go like this. All right, and now if my goal is to get S sub n by itself, yeah, we're good. What could I do now? Divide each side by 1 minus r. And I'm going to write that answer down here. So S sub n equals, let's leave my spell, I need some more space. S sub n equals a sub 1 minus a sub 1 r to the n over 1 minus r. And what does it have in the top in common? Is an a sub 1. So if you want, you could factor that out as well. And the way the book writes the answer is they factor an a sub 1 out, and they leave it like that. So S sub n equals a sub 1 times 1 minus r to the n over 1 minus r. That is the formula for the sum of a finite geometric sequence. That's what you just wrote down, so you don't have to write it again. I think the last thing we'll do is just finish up with a problem where we try that out. Okay, so there's only two things you need to use this formula. You need to know the first term in your sequence, and you need the common ratio. So let's start with the first term. What's the first term in that sequence? 2. What are we multiplying by each time? We're multiplying by 1/3. Just fill in those two numbers into that formula. So S sub n, I know they want 12, but I'm just going to write this first, and then I'm probably going to stop with that. So S sub n equals the first term times 1 minus r to the n, 1 minus 1/3 to the n, divided by 1 minus r. What's 1 minus 1/3? 2/3. So that's the formula to find the nth partial sum. So if specifically you want the 12th partial sum, you just have to plug in 12 for n and do it all out. Okay, just type it in on your calculator. Does anybody want me to type that in and do it out? Okay. What do you notice is happening as you move down the line? Each term is getting closer and closer to what number? Yeah, it's getting closer and closer to 0. So that's the second term, 2/3. That's the third term, 2/9. So eventually what's happening is the numbers that you're adding are going to be getting so small that if you were to find the 100th partial sum, it wouldn't be that much different than the 12th. Because by the time you get down to the numbers that are that far away, they are so small they don't even make a difference. So that kind of gives you a hint at maybe if you add up infinitely many terms, if they get small enough and they don't make a difference, that's actually something you can do. You can add up an infinite amount of numbers. Not by hand, but there is a way to do it. Okay, and that's what we'll pick up with tomorrow. Okay, so the homework tonight, it's on 601. And it's 1 through 17 all.